All right, so I want to now discuss the permutation groups. The permutation group here is S4. It's actually 24 elements. I kind of wanted to limit this to the 20 element and below groups, but the permutation group is so important. And S4 is really nice because 24 elements, it's actually a pretty chunky group compared to all the other ones we've studied. It's got generators and relations, which is cool, but if you actually look at the multiplication diagram that the Group Explorer gives to us, and here it is. It's 24 by 24, right? So you can't really see all of it on this screen. But if you blew up just this area, right, you would get this. I needed to do it to keep the text from being too grainy. But this is just one little corner of it, right? There's 24 elements here and 24 elements here. But you look and you see, despite the fact that the chart gives the generator A and the generator B, you don't see A's and B's, right? You would expect A to be here, maybe B to be there or somewhere else, and then every other element to be some, AB or AB squared or whatever, and every element would be expressed in terms of A and B. But that's not what they do here. Instead, they use this what's called cycle notation. And that's very special because of the nature of the group. This is the permutation group. S4 is the permutation group on 4 letters. Sn is the permutation group on n letters. So in order to get to the bottom of this and to see why this is so important, that they single it out with its own special notation, we need to study the permutations themselves, remind ourselves how cycle notation works, and see why this is so important. And then this is also really important for our eventual walk into representation theory. So let's begin by studying permutations. We're going to start with the set A that contains 4 words. Word 1, word 2, up to word 4. And the point is that these are just distinguishable objects, right? They're just distinguishable. And the first simplification is we're just going to identify that set with simply the numbers 0, 1, 2, and 3. Oops, 3. What's wrong with my 3s? 3. Now, we have to define what we mean by a permutation, and it actually is quite obvious. We're just looking for a mapping from A to A, and it's got to be bijective. And in order to be bijective, you must be both injective and surjective. And as a reminder, this means 1 to 1, and this means on 2. And because it's bijective, it's clearly invertible. So we have all these invertible bijective maps from A to A, and any such a map is called a permutation. So the way we actually define permutations has sort of evolved. We have different definitions, actually the definition is what I just said, but we have different mechanical ways of expressing this depending on exactly what you're doing. But the most common introductory way to do this is we just explicitly state the mapping, right? We say that 0 goes to, and then I'll pick another mapping, say 3, 1 goes to 2, 2 goes to 1, and 3 goes to 0, right? And these little arrows here indicate that the top row is going to the bottom row. So this would mean that sigma of 0 equals 3. Sigma of 2 equals 1, right? Sigma of 3 equals 0. And what we do is we do not include these arrows, and this object here is one manifestation or one way of expressing explicitly a permutation. Now, one of the reasons why we go from word 1, word 2, word 3, and word 4 to these numbers is that we can establish a convention that we'll just order these numbers from 1 to 3 on the top row, the domain row, so to speak. And then we could almost take the bottom row and we could just get rid of this top row. On the other hand, if we leave the top row, we have to understand that if we switched, say, this column with this column, we would have the same permutation because the mapping is all expressed by the vertical relationship. The horizontal things don't matter at all. So one way, the next simplification that we typically do here is we drag this into something called cycle notation. And cycle notation is very efficient because it allows us to break this down into the most tightest possible form to express sigma. So the way we create the cycle notation is if you start with the explicit mapping, you just begin at the beginning, or you could actually begin it anywhere, but let's begin with 0. And you say, okay, 0 is going to go to 3. So you start with 0, and you know that 0 goes to 3. Well, then, knowing that 3 has been replaced by 0, you know 3 has to go somewhere. So you look over here and you say, oh, 3 goes to 1. And you write down 1. Then you know that 1's been replaced, and so 1 has to go somewhere. So 1 goes to 2. You write down 2. And then you know that 2 has to go somewhere. Oops, did I really miss... Yeah, I screwed this up. That should be a 2. And 2 ends up going to 0. Now, when 2 goes to 0, 0 is already on this list, right? 0 has already been vacated at the beginning of the list. So we just close it. And then that cycle now represents this permutation, right? And the way we understand it is we simply say, okay, 0 maps to 3, 3 maps to 1, 1 maps to 2, and 2 maps back to 0. This whole thing is a little cycle. And this is a 4 cycle. A 4 cycle because it has 4 different elements of the underlying group. In this case, the underlying group only has 4 letters, so this 4 cycle is the largest cycle we could have. Now you can imagine another cycle, tau, which might be expressed using this mapping. This is the explicit mapping. And notice that this mapping, of course, doesn't move 2 and it doesn't move 3, and it just sort of takes 1 to 0 and 0 to 1. So if you did the same process, you would end up discovering that the cycle is 0, 1, and then 1 goes back to 0. 1 goes back to 0, so you close the cycle. And then you would say, okay, 2 goes to itself, and 3 goes to itself. So this is how you express in cycle notation the circumstance when some of the elements don't map map to themselves, map identically. When this happens, it is much more common to just omit it. Anything that doesn't show up in the cycle is assumed to just not map anywhere. So you don't need this. That's redundant. So again, you can get this very, very tight. And so the final cycle notation would be something as simple as 0, 1, and this is a 2 cycle. All right, so there's a 4 cycle, a 2 cycle, and you can easily imagine a 3 cycle, right? Whoops, let me change the color. You could easily imagine a 3 cycle where one item stays the same, one word stays the same, and then the other 3 change. And this would be 1 goes to 2, 2 goes to 3, 3 goes to 1. So that is a 3 cycle. So, simple enough. There's one other possibility here. So this is an important... So now once we start seeing that these cycles, we ask what kind of permutations can we have? Well, we can call this type of permutation a 4-cycle permutation. This type of permutation we could call a 2-cycle permutation, but we give it a word. It's called a transposition, right? And then we have a 3-cycle as a possibility as well. Are there any other possibilities? Well, if you think about it a little bit, if you have 4 letters, how many different ways can you divide up the number 4? You could divide it up as 1, 1, 1, and 1. This is sort of partition the 4, different ways of summing to 4. So you could add up 4 ones, you could add up 1 plus 1 plus 2, right? You could add up 2 plus 2, and you could just have, then you could also have 3 plus 1, right? And you could have 4. So each of these different ways of partitioning the number 4 should yield a type of permutation, right? We've already got the 4 cycle accounted for, so that would be this one, right? So we've already seen an example of that. We've seen an example of this, right? Because that's what a 2 cycle, that's what a transposition is. Because it's always understood that if you have 0, 1, then you have 2, and you have 3, and so that's 2 plus 1 plus 1 equals 4, right? But we don't show those, but they're there. So we've got that one. Likewise, we have the 3 plus 1, right? That's our 3 cycle. And this guy, the 1 plus 1 plus 1 plus 1, what would that be? Well, that would be just 0, 1, 2, 3. So that's and they'd all be crossed out, right? So we give that one a special name, right? Of course, that's the identity permutation. Right? That's the permutation epsilon, which takes 0, 1, 2, and 3 and returns 0, 1, 2, and 3. So that one's taken care of. The only one that's missing is this 2 plus 2 one, right? And the example of that would be, say, transposition delta, 0, 1, 2, 3, and let's see, 0 goes to 3, 3 goes to 0, 1 goes to 2, 2 goes to 1. And if there's that, this is just one possible example, of course. And if we do the cycling analysis of that, we see 0 goes to 3. So I start with 0, I go to 3, but 3 goes back to 0, so that closes. 1 goes to 2, and then 2 goes back to 1, and that closes. So this is delta in cycle notation, and that's an example of 2 plus 2. And there's no other possibilities of the different types of cycles. So this would be a pair, I guess we would say, a pair of 2 cycles. Now, an important thing to see, and this is supposed to be somewhat of a review. Presumably you've seen this before, but this is all kind of a reminder of how this works. But what is important is that given any permutation, right, given any permutation at all, when you break it up into the cycles, you'll never see a number in two different cycles. Now, in our case, so let's say we had n equals 10 elements, right? So the set A would really have 0 through 9 as our words, right? And then we can have many, many different cycle structures, right? Because all the ways of summing to 10 in different fashions. I'll just write some down. There are actually 42 different partitions, and 42 different partitions of, say, the number 10. I only know this because I looked it up. There's actually no formula. There's no known formula for the number of partitions of a given integer that I'm aware of. Last I understood it was still an open problem. If given an integer, how many different ways are there to partition it? But for 10, you certainly have the possibility of, well, let's see. I mean, you can do 5 plus 5, of course, right? But then you can do 6 plus 4. You can do 1 plus 1 plus 1 plus 7. I mean, all of those count. When you're all done adding all the possibilities up, you get 10. So what does this mean? Well, it means you can have double cycles of 5 things. I mean, you can have a pair of 5 cycles. You can have 3 pairs of 2 cycles. That would be 6, and then 1 4 cycle, right? That'd be 10. That's a possible cycle structure for a permutation. The point I'm trying to get across here is that given the size of the group that you're constructing the permutation for, all the permutations can be expressed as products of cycles. And what's really important to remember is the cycles are disjoint, right? That means that no element appears in any cycle more than one time. I mean, well, let's see. No element appears in this collection of cycles more than once. And of course, ultimately, you'll have 10 different elements, but we omit the ones that just have 1, so you don't even see those. Okay, so back to S4, we've identified all the different kinds of permutation cycle structures you could have. All right, so I've laid out a few quick permutations. I showed it in its classic permutation form, its explicit mapping, and then the cycle notation. And a couple quick reminders is that the cycle notation, if you take a permutation and you break it into its cycle decomposition, then you will discover a couple important points. One is that in the cycle decomposition, every word in the permutation, or every number in this case, just shows up once. So no 2 cycles, in this case, this is the only one that has 2 cycles, will ever have an element in common, right? So, you know, this, I guess, if we added these guys like that, you would see that every cycle is disjoint, right? There's no members in common. And that's really important because disjoint cycles commute. which is to say that this last cycle is the same as 1, 3, 0, 2. There's no distinction there. And likewise, the cycle itself is not 100% specified by the numbers in their order, because if we change the order to, say, 1, 2, 3, 0 or to 2, 3, 0, 1, right, that should work. It's the same process, right? If we look at any of these, what we see is 2 goes to 3, 3 goes to 0, 1 goes to 2, 2 goes to 3, 3 goes to 0, 0 goes to 1, 1 goes to 2, 0 goes to 1, 1 goes to 2. And that's the same here. 2 goes to 3, 3 goes to 0, 0 goes to 1, 1 goes to 2. So those are all the same. Now, we do need to know how to combine two different permutations, right? Because we're expecting that if we execute permutation, say, tau, on, say, one of the words, say the number 1, and then we executed gamma, right? We are expecting to get gamma of tau of 1. Well, tau of 1, if we look up here, tau of 1 is simply 2, right? So we're asking for gamma of 2, and gamma of 2 is 0, right? So gamma of 2 is 0. So we should be able to combine permutations to get this all in one fell swoop. And the way we would do that is we would write tau gamma, and we can just put down the cycle structure. We skip the 3 and the 0. We don't need those. And then gamma is 0, 3, 2. We skip the 1. We don't need that. And then we kind of read this way, right? So we'll start with, we can pick a number to start with in the first cycle. We'll start with 0. So we know that 0 goes to 3 in the first cycle, and then it's left alone in the second cycle. So we know that 0 goes to 3. And in the first cycle, 3 goes to 2. 3 goes to 2, and in the second cycle, 2 goes to 1. So ultimately, 3 goes to 1. And then and then the first cycle doesn't do anything to 1, but 1 goes to 2 in the second cycle. So we get 0, 3, 1, 2. And then 2 goes to 0 in the first cycle and is unaffected by the second cycle. So that completes our product. So the product is 0, 3, 1, 2. And I think the way we think about this is it's really tau after gamma. So we apply gamma first, which sort of explains why we go in this direction as our convention. All right, so now that we can multiply cycles, we clearly have to find the identity cycle, right? And the identity cycle, which is usually given by epsilon, is clearly 0, 1, 2, 3, 0, 1, 2, 3. And in cycle notation, it would be 0, 1, 2, 3, which is basically given by the open parentheses, right? And we saw, if you remember the multiplication table for this permutation group, we saw this open parentheses. So clearly that those numbers on the permutation group are the cycle notations for all the possible permutations of 4 letters. We'll be studying that a little bit more. Let's just push a little bit further. We do need to ask our question about the inverse permutation, right? So, for example, sigma sigma after sigma inverse should equal the identity. So how do we do that? Well, in this form, 0, 1, 2, 3, sigma is 2, 3, 0, 1, right? And the inverse, we just flip the rows in the column. We go 2, 3, 0, 1, 0, 1, 2, 3, like that. And this is sigma inverse. Now, we don't usually like to have the upper row sort of out of order, right? We like the upper row to be 1, 2, 3, 4. And as I said, we can change this arbitrarily. So we can write this as 1, 3, oops, not 1. It starts with 0, right? So it's 0, 2, 1, 3, 2, 0, 3, 1, right? So then we now can convert this to cycle notation. And in cycle notation, well, for cycle notation for sigma, we know it's 0, 2, 1, 3. 0, 2, 1, 3. But let's look at the inverse, right? this is sigma inverse, so we claim, and its cycle notation is 0 goes to 2 and 2 goes to 0, and 1 goes to 3 and 3 goes to 1. It's the same thing. It's its own inverse, right? And that's true for all transpositions. Transpositions are their own inverse. And we can quickly check this, right? We'll just start with, say, the number 1. 1 goes to 3 in this cycle. It's left alone here. 3 goes to 1 in this cycle, so 1 goes to 1. 0 goes to, well, let's see, hold on. 1 goes to 1, right? So 1 doesn't change. And then we could do 0. 0 is unaffected by the first cycle. It goes to 2 in the second. It goes back to 0 in the third. So 0 goes to 0. 3 goes to 1 in the first cycle, back to 3 in the third cycle. So 3 goes to 3. 2 goes to 0, and then back to 2. So 2 goes to 2. So this is clearly the identity cycle. This is 0, 1, 2, 3, 0, 1, 2, 3. So everybody has an inverse, right? So everybody has an inverse. We know that the product of a permutation is a permutation. You can show associativity. That's not a very difficult one. It's not commutative, though, but you can show associativity. And so all of the permutations on 4 letters form a group, and that group is S4. So now let's go back and look at the S4 picture again. All right, so now the multiplication table for S4 puts every possible permutation in cycle notation as the elements of the group, right? We know we have a group elements, we have multiplication on it, so this is the elements of the group. And we should see, for example, every possible transposition in this list somewhere, right? So here's the 0, 1 transposition, the 0, 2 transposition, 0, 3 transposition, and we see the 1, 2 transposition, 2, 3, and 1, 3 transposition. Let's see, is that all of them? And then here's the double transpositions that we were talking about. All of the possible double transpositions are in there. And then all of the possible 3 cycles are in here, right? And then we didn't talk as much about the 4 cycles, but there certainly are 4 cycles. Here's a 4 cycle, and here's a 4 cycle, and these guys are all 4 cycles. And so every possible element of the group is there, and this is the identity element. So the multiplication table is simply it'd be interesting to see. Is it the row, is AB given as B is the row and A is the column? We can check that pretty fast, right? Let's go to this, let's go right here, and let's look at this 4 cycle, 0, 3, 2, 1, multiplied by this guy, 1, 2, 3, right? So this is the column by the row, with column on the left, row on the right. So what would the result of this be? Well, let's see. So we'll start with 0 goes to 3 in the first cycle, 3 goes to 1 in the second cycle, so 0 ends up at 1. 1 goes to 0 in the first cycle and stays there in the second, so we have this transposition. 2 goes to 1 in the first cycle, and 2 goes to 3 in the second, so 2 goes to 3. And 3 goes to 2 in the first cycle, and 2 goes to 3 in the second cycle. Wait, what did I do wrong? Oh, right. 2 goes to 1 in the first cycle, and then 1 goes to 2. So 2 kind of gets stuck by itself, and 3 gets stuck by itself. So the column row version of this would be just the just the transposition 0, 1. Now, if the table works the other way around, it would be 0, 3, 2, 1, 1, 2, 3, right? And that would equal the 0, 3 cycle like this. So let's see, what is the actual answer? The actual answer is, let me draw it here, 0, 1, which is the first case. So they're doing column on the left, row on the right. Okay, fair enough. So now we know why we know how these guys are identifying this group with they're being very literal, right? The S4 is the group of permutations of 4 letters, and they're showing literal permutations, right? But this could be done symbolically, right? In fact, if we go to our table, we see right here that S4 actually has a construction by generators, right? It is, right? Its generator construction looks like this, right? And in fact, there's another generator construction out there. This is sort of a minimal one. Right? This shows that there are 2 generators that can generate all of S4. But there's another way of generating, there's another rule that'll generate any of the permutation groups. So let's have a quick look at that. So this starts by saying, the way we do this is we say we're going to take a generator, we're going to call the generator a sigma, and we're going to give sigma an index. So there's going to be, there's going to actually be, for Sn, it's going to turn out there's n minus 1 generators. So I is equal to 1 all the way to n minus 1. So sigma I is going to be one of these generators. And the rule is that sigma I squared is the identity element. So that is an involution. Let me make my identity element epsilon. So every one of these generators is an involution. And that should give you a hint about what's going on, because remember, these 2 cycles are all involutions. So every generator is its own inverse. And then we say that sigma I commutes with sigma j if I does not equal j plus or minus 1, right? So what we're saying is that j has to be, it can't be adjacent to I and j cannot be 2 adjacent numbers in this list, right? So if I equals 3, then j cannot equal 2 or 4, right? And likewise, if j equals 6, then I can't be 5 or 7, right? So otherwise these commute, right? So this rule applies when these indices avoid this kind of collision. It's a near collision, right? So there's that rule, and then there's one more relation which goes like this. It's kind of a little awkward relation, but if we took an example, we might say sigma 1, sigma 2, sigma 1 equals the same thing as sigma 2, sigma 1, sigma 2. And if we understood sigma to be transpositions, right? If we understood them to be transpositions, we might think, okay, if sigma 1 is a transposition between 0 and 1, sigma 2 is a transposition between 1 and 2, sigma 1 is a transposition between 0 and 1, that should be the same as this expression, right? And as long as this is true for all of your sigmas, the sigmas will generate the entire permutation group. It's another way of saying that all permutations can be written as a product of 2 cycles, right? That's what, when we, this sort of generator relation that we're putting down here, that's what they're saying. Let's, by the way, check the math on this one. If 2 goes to 1, 1 goes to 0, and then in the end it's, and then the last, the first, all right, so the first cycle takes 1 to 2, and the second cycle does nothing, and then the third cycle takes 2 back to 1. So this just gives you 1 to 1. 0 is unaffected by the first cycle, converted to 1 by the second, and then 2 by the third. So 0 goes to 2. 2 goes to 1 in the first cycle, 1 goes to 0 in the second cycle, so that closes this cycle out. And that is, that's everything that happens in the cycle. So that's 0, 2 on this side. On this side, we get 1 goes to 0 in the first cycle, 0 is unaffected by the second, and then 0 goes to 1 in the third cycle, so 1 doesn't change. 0 goes to 1 in the first cycle, 1 goes to 2 in the second cycle, and is unaffected in the third, so 0 goes to 2, and you can see that 2 is unaffected in the first cycle, And the second cycle, 2 goes to 1, but 1 goes to 0, so that closes that out. So, in fact, those are the same for these transpositions. The point is, these generators, I'm just trying to demonstrate that this is the formal way of saying that if you create all of the transpositions in sequence, you can build any member of the group, because those will generate the group. It's a bit of a messy generator, right? Because it seems like there's n-1 generators for the group. If we look at S4, for example, in S4, what would we have? So here what we see is, okay, for S4, following this prescription, we have 3 generators, because we're expecting n-1 generators, right? n-1 generators. And we'll call them sigma 1, sigma 2, sigma 3. They're all involutions. That's this statement. And they commute when I and j are not adjacent. So the only 2 that are not adjacent are 3 and 1. So these 2 would commute. And then if they don't commute, you have this expression. Well, there's only one way to get that expression. Well, I guess there's 2 ways, actually. There's this way here, right? And then there's also, I didn't write it down. I should have 2 sigma 3 sigma 2 equals sigma 3 sigma 2 sigma 3, like that. So there's 2 of those guys. So this guy applies twice. And that is the generator and relation formula for this group. So now every group out there would just be a collection of words written in sigma 1, sigma 2, and sigma 3. So you might have, presumably there's a permutation out there that looks like, let's just go with sigma 1, sigma 3, sigma 2, sigma 1, sigma 1. And then you would look at that and say, okay, well, that's the identity. And then you have sigma 1, sigma 2, sigma 3 is left. Do any of these relations apply to sigma 1, sigma 2, sigma 3? Well, you have sigma 1, sigma 3, they commute, right? So you could say, well, this is the same as sigma 3, sigma 1, sigma 2. And then you could look at, well, let's see, sigma 1, sigma 2, if you multiply on both sides by sigma 1, you get sigma 1, sigma 2 equals sigma 2, sigma 1, sigma 2, sigma 1, and that doesn't really help you. So this might be an example of another group element formed by these generators. But if you were to roll up this word and you had, say, in here sigma 1, sigma 2, sigma 1, like that, then you know that this could be replaced at least by that, I suppose, right? And ultimately, one way or another, you can produce all of the different permutations using this formula. Now, this is very abstract now. You no longer are really treating it like permutations. But if we set them up as such, if we said sigma 1 was 0, 1, sigma 2, well, sigma 1 would be 0, 1, sigma 2 would be 1, 2, and sigma 3 would be 2, 3. That would work, right? Those 3 transpositions are all you need to create any permutation. Now, how does this compare with what they actually did on the Group Explorer? All right, so the Group Explorer for the Group S4, I can't blow this up anymore for some reason. Oh, there we go. I was able to do it. It shows what you see for the Group Explorer for S4 is you see this generator relation for S4. I'll underline it here. 24 group. This is it. So it's A4 equals B cubed equals 1, and then BAB equals A inverse. So I put that on a sheet over here. A4 equals B cubed equals 1, BAB inverse. And that's the generator from the Group Explorer. And this one down here is the one that I showed you just a moment ago. Now notice this one has 3 generators, and this one has 2. So clearly this is less efficient in some way than this one. But we should be able to produce this generator relation from these because they're all just generators. So I should be able to find an A and B that I can construct out of these sigmas that satisfy these relations. So let's give that a try. So the way I'm going to approach this is first looking at this relation. I'm going to take this A inverse over here and I get AB equals epsilon, or AB squared equals epsilon. So whatever A and B are, their product is an involution. So right away, that means their product has to be a 2-cycle. I shouldn't use A and B. A 2-cycle, like X and Y, say, or no commas, right? 2-cycle like X, Y, or it could be a pair of 2 cycles, X, Y, Z, W, right? So any of those things would be a sufficient involution to make this work. And then if I look over here, I see A to the 4th. Well, you might think, well, A to the 4th could be an involution too, but that's usually not what this thing means. This doesn't mean like, they would have said, if that was the case, they would have gone with A squared equals epsilon, right? If that was supposed to be an involution. So it's not. So we need a 4-cycle here. This is going to have to be an X, Y, Z, W, some kind of 4-cycle there. And then this is going to have to be a 3-cycle, this B. So I'm good with involutions, and I'm good with this 4-cycle, right? Because the 4-cycle is going to be the product of 3 2-cycles as long as they all share something in common. So 0, 1, 1, 2, 2, 3, that's going to produce the 4-cycle 3, 0, 1, 2, which is 0, 1, 2, 3, if we shift it. So if you have 3 1-cycles where they're just sharing one element in common, that'll produce a 4-cycle. And this is how we model our sigma 1, sigma 2, and sigma 3, by the way. So for A4, that's what we're going to choose. We're going to choose sigma 1, sigma 2, sigma 3 equals A. And sigma 1, sigma 2, sigma 3 should, when raised to the 4th power, right, should be epsilon. So we'll check that. And then AB has to be an involution. So we can choose one of our 3 sigmas for AB. So AB will be, say, we'll call it sigma 1. Now, it could be sigma 1, sigma 3, but we're going to try sigma 1 first. So here is our check of sigma 1, sigma 2, sigma 3. We lay it all out there, and we use the associative rule to get rid of the parentheses. So after we remove the parentheses, we just sort of look at what we got. And we've only got these 2 relations down here to work with, so it's not too difficult to see what the next step is going to be. We're going to, well, we have the 3 relationships, right? So we're going to, the first thing we're going to do is commute 3 and 1. So we'll start seeing things like 1, 2, 1 and 3, 2, 3, where we can start playing with those. And when we do that commutation, indeed, we see 1, 2, 1, we see 3, 2, 3, we see 1, 2, 1, and 3, 2, 3. So I'm going to replace, actually, I think replacing all of them is the way to go, right? If 1, 2, 1 went to 2, 1, 2, and 3, 2, 3 went to 2, 3, 2, then the 2's would be together, and because they're involutions, they would cancel. So let's do that, and sure enough, right, I switched each one from 1, 2, 1 to 2, 1, 2 using this rule, and 3, 2, 3 to 2, 3, 2 using this rule, and sure enough, you see all of these pairings of these 2's. So let's see, I guess you would cross out that pairing, and that pairing, and that pairing. And then you see this 3 and 1, which we can flip to make that a 1 and a 3. And then you have this pairing and that pairing. And then this last one was a 2, right? There should be a 2 there, and then that will cancel with that. And you will, in fact, get I. So we've made a functional choice for A. A is going to be functional, meaning we check that it works. Sigma 1, sigma 2, sigma 3. Using this abstract set of rules, we've duplicated, we found an element at least that's eligible to be A4. Now there are other versions, like sigma 2, sigma 3, sigma 1 probably would have worked, right? And sigma 3, sigma 2, sigma 3, sigma 1, sigma 2 would have worked. But we're going to go with sigma 1, sigma 2, sigma 3. So now, now let's check and try to figure out what we can do about this rule. See, this to me, remember, AB is just another group element, right? So we could treat that as though it were a generator. And so we can look for AB, and knowing A and AB, then we can kind of surmise what B could be. I just have this is easy because I can think, oh, this has just got to be an involution. So I'm going to make my initial try just sigma 1. That's just sigma 1 equals AB, right? And we're done. Let me erase this stuff and we'll try it. So we nominate sigma 1 as equaling AB. So we now know that sigma 1, sigma 2, sigma 3 times some unknown thing B equals sigma 1. All right, well, that's not too tough, right? If we take B equal to sigma 3, sigma 2, then this should work. Well, does sigma 3, sigma 2 satisfy B cubed equals 1? Sigma 3, sigma 2, sigma 3, sigma 2, sigma 3, sigma 2. And then we do 3, 2, 3 becomes sigma 2, sigma 3, sigma 2. And then those two cancel, right? And those two cancel. And what happens next? And, the way I drew this was just bound to cause confusion. So let me do this again. Okay, so sigma 3, sigma 2, sigma 3, sigma 2, sigma 3, sigma 2. We take these guys and we replace it with sigma 3, sigma 2, sigma 3. Oh, this is written incorrectly. This should be sigma 2, sigma 3, sigma 2, right? And we replace this with, let's see, sigma 2, sigma, let me get this right, sigma 2, sigma 3, sigma 2, like that. And then what we see is that clearly this cancels, that cancels, and then what's left are these two sigma 3s, and those cancel. So we have actually found we have actually found the connection between this set of generators and this set of generators. And I did this because, the Group Explorer is just one resource, and they've chosen this particular set of generators. I think the reason, the whole point of all this is all the symmetric groups. So if you have a symmetric group of n, right, you can generate it with a whole bunch of transpositions. N minus 1 transpositions will generate the group using these rules, right? When there's more transpositions, you end up with more of these relations. It becomes quite a mess. But you can also generate the symmetric group with one n cycle that goes from 1 to n, and then a transposition 1, 2, right? Those two elements are sufficient, right? And interestingly, this captures that a to the 4, right? This would become a to the n for Sn, and you would still need this one transposition a squared b equals 1. But not every 2-cycle will work, right? You've got to have a 2-cycle of adjacent elements. Anyway, adjacent elements, if you use this as your n cycle, then you'll need a 2-cycle with adjacent elements. That would be the only way to satisfy all of these requirements. But this was just a bit of an exercise in using these generators. Okay, there's a lot more to say about the symmetric group than this, a ton more. But this is getting us familiar with it. If we go back to, there's a whole bunch to say about the subgroups and about the significance of the symmetric group in the overall aspect of group theory and representation theory. But we got our feet wet a little bit. And we see the group grows really fast. So S4 is pretty bulky. But there you have it. And we will now, we'll start talking about all of the different kinds of subgroups and other critical facts about group theory that we have to remember before we can really get into representation theory. So that'll be next. So see you next time.